Hey everyone, welcome back to the channel. Today we are diving into the fascinating world of Netflix system design. Ever wondered how Netflix seamlessly streams your favorite show to millions of users globally without buffering or delay? In this video, we will break down Netflix architecture, its components, and the clever engineering that powers the platform. So grab your popcorn and let's get started. Okay. So at its core, Netflix is a video on demand streaming service, but under the hood, it's a highly distributed, available, and performance critical system. Netflix has over 230 million subscribers worldwide. That means it has to serve millions of video streams simultaneously, 24 by 7, across different network speeds, devices, and regions. To support this, Netflix uses a combination of cloud infrastructure, microservices, CDN, adaptive streaming, and more. So let's get started. So let's start with the functional and non-functional requirement, right? So, when we think about functional requirements, so user should be able to stream and share videos. The content team should be able to upload new videos like movies, episodes. User should be able to search for videos using titles or tags. User should be able to comment on a video similar to like in YouTube, right? And let's say for example we are watching video in Netflix and suddenly we have to go somewhere, so we moved I mean we shut up the system, but again we come back and start the same video, so it resumed from where we left, right? So basically resume video playback from the point user left off. So these are the functionalities which comes under functional requirements. So now let's discuss about non-functional requirement. So system should be highly available with minimum latency, so that the video should not lag, right? And it should be highly reliable. Ensure none of the video being lost or corrupt. So the none of the scenes should be lost while we are streaming the videos, and it should be scalable and efficient and provide users with experience of real-time video streaming without any lag, right? So these are the functional and non-functional requirement. So let's now go to estimation and constraints. So before proceeding to system design diagram, we should always know what is what are the constraints and how much storage or how what will be the bandwidth that we'll be considering before estimating our system, right? So while discussing on this, maybe you should make sure to check any scale or traffic related assumptions with your interviewer, right? If interviewer tells you to assume yourself, then maybe you can start assumption, right? So first of all, let's start estimation of traffic. Okay, so this will be a Netflix mostly will be a read heavy system. Okay, let us assume we have 1 billion total users with 200 million daily active user, and on average each user watches 5 videos a day. Generally it is not 5 videos, but I have taken this 5 videos so that the multiplication will be easier, right? So this gives us 1 billion videos watched per day. Okay, so 200 million daily active user into 5 videos, it will be around 1 billion videos watched per day. So it is around 1 billion requests per day, which gets translated into 12,000 requests per second, right? So per second, we are getting 12,000 requests to our server. So this is related to traffic. Now let's move to storage. So how much storage we need to consider while designing our system? Okay. So again, we have to assume like how much space is occupied for each movie on an average. So if we assume each video is 100 MB on average, we will require about 100 petabyte of storage every day. Why? Because we are receiving 1 billion, I mean, 1 billion requests per day, right? 1 billion, and each request Each request will be for any movies or series. So we are on average we are considering like each movies or series will be of 100 MB. So it will be around 10 ki power 9 into 100 MB, and it will be around 10 ki power 9 is 1 petabyte. So 100 petabyte, right? So we need 100 petabyte of storage every day. So now let's go to bandwidth. So as our system is handling 100 petabyte of ingress every day, we will require minimum bandwidth of around 1 terabyte per second. How? Let's see. So 100 into 10 ki power 9 is like 100 petabyte, and now we are converting from day to second. So we are dividing by 24 into 60 into 60. So it will be around 1 terabyte per second. Okay. So we need a bandwidth of 1 terabyte per second. So high level estimate we have done, and here is our high level estimate. That is, we have a daily active user of 200 million. Now request per second is 12,000 per second, and the storage per day is 100 petabyte. And for 10 years, it is around 365 into uh, 10 ki power 3 petabyte, and bandwidth will be 1 terabyte per second. So this is our high level estimate. Now let's design our system according to it. So before proceeding ahead, let's consider uh, which type of database we'll be using, right? So before designing, we should know that which kind of database we will be using. So we can use a relational database such as PostgreSQL for payment related transactions, right? And distributed NoSQL database such as Apache Cassandra for video related info. Okay. And if we consider a high level design, okay, so let me show you the diagram. Yeah. Okay, this is okay. So if we consider high level design, okay, so we'll be using there are two types of architecture as we know, monolithic and microservices. So we'll be using microservices architecture since it will make it easier to horizontally scale and decouple our services. Each service will have ownership of its own data model. So let's try to divide our system into some core services. So here you can see in the diagram, we have stream service, search service, user service, media services. So user services, this service basically handles user related concerns such as authentication and user information. This is a stream service. The stream service will handle video streaming related functionality. This is the search service, is responsible for handling search related functionality, like when we visit Netflix and we try to search any movie with a different tag, right, or with hero name. So it shows all those movies according to the search, right? And this is the media service. This service will handle the video upload and processing from the content team. And this is analytics service. This service will be used for metrics and analytics use cases, like since uh, Netflix is used worldwide, so it needs to track all these services so that it will know from which service, like what is the performance of each services, right? And so there are so let's first discuss about this video processing pipeline. So what is this? Okay. So here is how we can process videos once they are uploaded by the content team and are queued for processing in our message queue, right? So once our content team upload the start uploading video to media service, right? So there is a queue which uploads this media to the video processing pipeline. And inside video processing pipeline, there are four components, that is file chunker, content filter, transcoder, and quality conversion, right? So let's discuss each one by one. So file chunker, let's discuss how this works. So this is the file chunker. This is the first step of our processing pipeline. File chunking is the process of splitting a file into smaller pieces called chunks. It can help us to eliminate duplicate copies of repeating data on storage, and reduces the amount of data sent over the network by only selecting change chunks, right? So now let's move to content filter. This step checks if the video adheres to the content policy of the platform. This can be pre-approved in the case of Netflix as per the content rating of the media, or can be strictly enforced like YouTube. So at different geographical location, basically there are various restricted content, right? For example, pornography or drugs related thing. So basically, with the help of content filter, basically we filter those chunks. So now let's move to transcoder. So basically transcoding is a process in which the original data is decoded to an intermediate uncompressed format, which is then encoded into the target format. This process uses different codecs to perform bitrate adjustment, image downsampling, or re-encoding the media. And the last is quality conversion. So basically, this is the last step of the processing pipeline, and as the name suggests, this step handles the conversion of the transcoded media from the previous step into different resolutions, such as 4K, 1080 pixel, 720 pixel, right? Because every user will be having different bandwidth or different network, like some will be having slow, some 3G, 4G, right? So accordingly, we have to store the quality of the video to distribute according to the different bandwidth, right? Okay, now let's talk about video streaming. So, video streaming, this is the streaming service. So, video streaming is a challenging task from both the client and server perspectives. Why? Moreover, internet connection speeds vary quite a lot between different users. To make sure users don't refresh the same content, we can use a content delivery network, that is CDN. And Netflix takes this step further with its Open Connect program. In this approach, they partner with thousands of internet service providers to localize their traffic and deliver their content more efficiently. So here in the picture, you can see this is the ISP. When user requests any movie or content, so the request goes to internet service provider. So basically, what Netflix has done is they have installed their own Open Connect appliances. It is not CDN, but it is almost like CDN, which is installed near ISP. So basically, they have provided infrastructure, Netflix, to the ISP, and they basically cache the most frequent, uh, most frequent traffic within that local area. For example, let's say in India now the rate to movie is quite. I mean, it is quite popular. So when uh, when it comes to OTT platform, so I mean the people might search more this movie, right? So what Netflix do, basically they cache, they put the I mean this movie inside the Open Connect appliances, which caches this movie, and whenever user request it, basically it see first Open Connect appliances, and if it is present there, then the traffic is redirected to here, and again uh, from I mean from OCA only, the user will get all those content. So which reduces a lot of network bandwidth, and it reduces latency as well, right? Because we are not sending requests to this database again. This all the process are not involved in between, so it directly fetching from the OCA. Okay, so this is the advantage of Open Connect appliances, which is installed near ISP. So now let's discuss about the search service. So sometimes traditional DBMS are not performant enough. We need something which allows us to store, search, and analyze huge volumes of data quickly and in near real time, and gives results within milliseconds. Like Elasticsearch can help us with this use case. So what is Elasticsearch? It is a distributed. Here we can see we are using Elasticsearch. So basically, it is a distributed free and open search and analytics engine for all type of data, including textual, numerical, geospatial, structured, and unstructured. It is built on top of Apache Lucene. Okay, so so the question arises: how do we identify trending content, right? So trending functionality will be based on top of the search functionality. We can cache the most frequently searched queries in the last seconds and update them every seconds using some sort of batch job mechanism. So these all kind of activities is done by search service. Okay. So now let's move to data partitioning. So as you know, Netflix is, I mean, it is spread across global. So data partitioning is very important, so that we don't have to reduce the network traffic and delay. To scale out databases, we will need to partition our data. Horizontal partitioning, aka sharding, can be a good first step. We can use partition schema such as hash based partitioning. There are different kind of partitioning like hash based, list based, or range based composite partitioning. So we can these the above approaches can still cause uneven data and load distribution. We can solve this using consistent hashing. Okay. So now the question arises. I mean, Netflix has a lot of content, but it don't need to make it available to all the country, right? In some country, some contents are blocked. So basically, there is a term called geo blocking. We can determine the user's location either using their IP or region settings in their profile. Then use services like Amazon CloudFront, which supports a geographic restrictions feature, or a geolocation routing policy with Amazon Route 53 to restrict the content and reroute the user to an error page if the content is not available in that particular region or country, right? So recommendations is like Netflix is a machine learning model. Yeah, I mean, I mean, when you log into Netflix, you get a lot of recommendations. Like, so basically, Netflix uses a machine learning model which uses the user's viewing history to predict what the user might like to watch next. An algorithm like collaborative filtering can be used. For example, let's say you have watched any action or thriller movie, right? So it might suggest content related to that, so that you can watch next, right? So this is done by recommendation algorithm. And Netflix also uses use metrics and analytics. Reading analytics and metrics is one of our extended requirement. We can capture the data from different services and run analytics. Like here is an analytics service, and on the data using Apache Spark, which is open source. So here we are using a Spark. So what is Apache Spark? It is an open source unified analytics engine for large scale data processing, right? So Netflix has a huge amount of data. So to process that, we are using Apache Spark, which is analytics engine. Additionally, we can store critical metadata in the views table to increase data points within our data. Okay, so now let's discuss caching. Caching is very important. So in a streaming platform, caching is important. We have to be able to cache as much static media content as possible. To improve user experience, we can use solutions like a Radish or Memcached. But what kind of cache eviction policy would be best fit our needs? So the interviewer might ask you which cache eviction policy to use. So least recently used can be good policy for our system. In this policy, we discard the least recently used key first. So here, sorry, in the diagram you can see, uh, all the most of the load balancer is connected with the cache. Here you can see, because whenever we get request, first of all we try to find in the cache, and if it is not available, then we hit the database, right? So cache plays a vital role to reduce the latency. Now comes to media streaming and storage. So as most of our storage space will be used for storing media files such as thumbnails and videos, per our discussion earlier, the media service will be handling both the upload and processing of media files. We will use distributed file storage such as HDFS, cluster FS, or an object storage such as Amazon S3 for storage and streaming of the content. And last but not least, CDN, right, which you are using here, content delivery network. So it increases the content availability and redundancy while reducing bandwidth cost. Generally, static files such as images and videos are served from CDN. We can use services like Amazon CloudFront or Cloudflare CDN for this use case. And yeah, so this is pretty much we have so yeah, and that's a wrap on Netflix system design. If you found this video helpful, make sure to like, subscribe, and hit the bell icon so you never miss another deep dive. Also, let me know in the comments which system you want me to cover next, maybe YouTube, Instagram, or Spotify. Thanks for watching, and I will see you in the next one.